This is David Williams, and in this video I want to show you how a full wave bridge rectifier works. Now I'm going to redraw the rectifier here because I want to include transformer, which is something you'll normally see. And let's say this was a wall outlet, which is going to be a 170 volt peak signal at 60 hertz. And I've got my transformer here, and let's say this is a 10-to-1 transformer. So if this is 170 volts on this side will be a tenth of that, so we're looking at 17 volt peak. And then we come to the bridge rectifier part of the circuit. With this array of 4 diodes. And if you're actually building the circuit on a breadboard, it can actually sometimes be a little bit tricky to figure out how it works, or to figure out how the connections go. But it just takes some careful attention to detail and watching the polarities of your diodes, and you should be able to figure it out. And connected over here we have the load resistor. So let's figure out how this particular circuit works. We're going to have to look at 2 halves of the input AC signal. So if we have 170 volts peak coming in, we're going to have 17 volts across there. So let's just draw out that input signal over here. Okay, there's one full cycle, and then it's just going to repeat itself over and over and over again. So let's take a look just at the positive half of that cycle. So that's where this side is going to be more positive than this side. And once this becomes more than, actually as it turns out, it's going to be more than about 1.4 volts, assuming these are 0.7 volt silicon diodes, then some of these diodes are going to become forward biased and some will be reverse biased. So let's take a look at what's going to happen. We'll follow the path of conventional current here. So conventional current is going to go in this direction and come to this junction. Now, this diode is reverse biased, so current will not go through that diode. This diode will be forward biased, so current will go through that diode. We come to this point, current again can't go into that diode, so it can only go through the resistor back to this point. Now it looks like current could go through either one of these diodes, but remember we have dropped in voltage by going through this diode and through this resistor, so the voltage at this point is higher than the voltage at this point, so that diode is actually reverse biased. No current can go through it. Only path for current to go will be through this diode and then back to the transformer. So we'll have current that goes in that direction. And you'll note over here on the across this load resistor, current goes in the downward direction, so the top of the resistor is going to be at a higher voltage than the bottom of the resistor. And so what's going to happen if we were to plot out the voltage across that particular across this load resistor is the voltage across this load resistor is going to follow the input voltage, except because of these 2 diodes here, we will have 0.7 volt drop and 0.7 volt drop, so we'll have about 1.4 volts less. So over here, the voltage across the load resistor will look something like that. So we call that VL. And call that VL. Call that VIN, which is the voltage from this on the secondary side of this transformer. Now, on the negative half of the cycle, so this half of the cycle, which will be when the voltage on this side of the secondary is higher than the voltage on this side of the secondary. So what that means is current will go in this direction, come to this junction here. It can't go that way. It's going to have to go this way through this diode, come to this junction here. Can't go that way. It's going to have to go through the load resistor. Return back to the bridge here. come to this junction. Now, it looks like it can go through this diode, but remember this diode is reverse biased because the voltage over here is higher than the voltage over here, so it must go through this diode. At this junction again, it looks like it could go through this diode, but the voltage on this side is higher than the voltage on this side, so it's going to go in this direction and make a complete circuit there. Now, if we follow the path of the current back to the load resistor, current is going that direction, which means the voltage on that side of the resistor must be higher than the voltage on that side of the resistor. The exact same orientation as it was for the positive half of the input. So what that means is, adjusting for the diode drops across the resistor, we are going to get the same basic shape, well, it should be the exact same shape for the negative half of the input. Regardless of whether the input's in the positive half or the negative half, we should get a blip looking something like this for the voltage across the load resistor. So what we've done is we've taken an AC signal that was positive and then negative and turned it into something that is only positive. So we've rectified it, we've created a DC signal. And as a reminder of the magnitudes, if that point there is 17 volts, then this point here, the peak of the output, will be 17 volts minus the diode drop of 2 diodes. There's 1 diode drop, there's 2 diode drops, so it's going to be minus 1.4 volts. Gives us a total voltage at the peak of 15.6 volts. So this rectifier does create a DC signal from an AC signal, but it's not a particularly good DC signal because it's not constant. Typically you want your DC signal to be constant. Trying to power a microcontroller or something like that at 5 volts, you want it to be at 5 volts, not varying between 5 and 0 volts. So we need to add some stuff, at least one other component here to this circuit to make this a much better AC to DC converter. And at the very least, what the circuit needs is a capacitor. What that capacitor is going to do is act as a storage for energy to effectively filter the signal so it doesn't ripple as much, doesn't ripple between 0 volts and the peak. And I'm going to redraw the AC signal here. So here is my input AC signal. And then without the filter, what we're going to get is our DC signal with this monstrous ripple of 0 volts up to the peak. If we put that capacitor in, what's going to happen is on this, as the voltage is increasing on this, on the voltage across the load resistor, as that's increasing, the capacitor will also be charging. So it gets up to this point and the capacitor is going to be pretty much fully charged, because what's happening is that capacitor is charging through effectively no resistance. Here's my source voltage applied directly across the capacitor. It's just going to be experiencing the resistance of the wires. So the time constant is going to be fairly small. Now, on the downward part of the cycle here, the capacitor is now going to be at a higher voltage than the input signal, and it's going to start acting like a source. And so what's going to happen is now the time constant is much bigger because it's acting as a source to this load resistor. So the time constant is going to be based on the value of that load resistor and the capacitor. So depending on the capacitance and what the load resistance is, it's going to filter the signal out. It's going to filter the signal in some manner to get rid of this major ripple here. And then as the input signal climbs again in voltage, the input signal is going to climb above what the capacitors drop down to, and now the capacitor is going to be charging through this part of the cycle, and then the capacitor is going to discharge. And so what you'll end up with is something looking like this. And you see there's still some amount of ripple, but it's much less than it was before. So the ripple is the whatever the voltage is between those 2 points. And that ripple can be reduced by increasing the capacitor value. And it can be shown that that peak-to-peak ripple is dependent on the resistance, the capacitance, as well as whatever your peak voltage is. So I'm going to write out the equation for it here. It's beyond the scope of what I want to show in this video to show you where this equation comes from. So there's the equation for the peak-to-peak ripple, where that peak-to-peak ripple is that value. Vm, sorry, is not that one, but this one. Vm is that value, that peak value. RL is the value of the load resistor. C is the value of the capacitor. And T is the period, so that depends on the frequency. It's the time for 1/2 of a full input cycle or 1 full load resistor cycle. So just to show you a simple example, let's say that that load resistor was 220 ohms. The capacitor was 1,000 microfarads. The peak here, just like it was in the previous example, Vm is 15.4 volts. And it's a 60 hertz signal, so T is 1/2 of the period of a 60 hertz signal, so it is 8.33 milliseconds. So therefore the peak-to-peak ripple is going to be equal to 2 times 15.4 volts divided by 1 plus 2 times 220 times 1,000 microfarads, and this is all divided by 0.00833 seconds. And if you plug that number into your calculator, you get 0.57 volts. So that ripple is 0.57 volts, which is about 4%, 3.7% of the full Vm. So I hope you learned a little bit about full wave bridge rectifiers, and I will see you in the next video.